8,000 plus students, 400 plus faculty, 3,000 plus placements, 100 plus companies. Green campus with latest infrastructure. Industry institute collaborations. Techno and cultural fests. Ranked among top engineering colleges in the state, SB Engineering College for Women is now SBEC with co-education. SB Colleges, Tirupati. SB Colleges, Tirupati. 8,000 plus students, 400 plus faculty, 3,000 plus placements, 100 plus companies. Green campus with latest infrastructure. Industry institute collaborations. Techno and cultural fests. Ranked among top engineering colleges in the state. SB Engineering College for Women is now SBEC with co-education. SB Colleges, Tirupati. SB Colleges, Tirupati. 8,000 plus students, 400 plus faculty, 3,000 plus placements, 100 plus companies. Green campus with latest infrastructure. Industry institute collaborations. Techno and cultural fests. Ranked among top engineering colleges in the state, SB Engineering College for Women is now SBEC with co-education. SB Colleges, Tirupati. SB Colleges, Tirupati. 8,000 plus students, 400 plus faculty, 3,000 plus placements, 100 plus companies. Green campus with latest infrastructure. Industry institute collaborations. Techno and cultural fests. Ranked among top engineering colleges in the state, SB Engineering College for Women is now SBEC with co-education. SB Colleges.
Good afternoon to one and all present here. This is first day, second session of our program on second phase, nanotechnology and functional materials. Thank you for joining with us. Now I request all the participants to mute your audio and switch off your camera for smooth conduction of this program. Now let me introduce our resource person to the participants. Today's session, our resource person is Dr. K. Venkateshwara Rao. He has pursued doctoral research work in Johns Hopkins Medicine, USA. He has published more than 125 journals in international and national journals. He has published more than 15 books and published conference proceedings more than 80. He has achieved a patent too. His research projects are UGC 2 and DST Cell 1 and Nanomission 1 and Indo-Japan 1. These are the projects are applied Indo Sri Lanka and EMR Cell 1. His specialization of research are nanomaterials, synthesis and characterization, applications of energy, solar cells and batteries, sensors, gas, glucose and humidity, agriculture area, seed germination, biomedical, cancer imaging. He is the advisor for thesis advisor as a postdoctoral. One person has completed and PhD was awarded nearly 7 projects are ongoing and 128 MTech students were awarded under his guidance. Still 15 students are pursuing. Under his guidance, he has guided MPhil 1 awarded and MSc 10 awarded. He is the member of different board of studies and committees like JNTU for nanotechnology and physics. Now I request our resource person to proceed our session. Sir, requesting sir.
Thank you very much for introducing and given an opportunity to talk. I assume, are you able to see my screen?
Yes, sir. Yes, sir. Perfect, sir. Please proceed.
Thank you very much. I thank the college authorities and head of the department, mechanical engineering, and other faculty members who introduced me. Thank you very much. Very good afternoon to one and all. I assume most of them are mechanical background. So most of the things I'll be talking about materials and applications of sensors. In the meantime, because you are all mechanical background, if any questions are there, try to you can message such that the coordinator can see and ask that questions in the middle also, so that I can answer or I can make you feel comfortable. Okay, is it okay? And now,
okay, sir. Thank you. Thank you.
Thank you. So now, before I'm going to start my talk, let me give 4 or 5 takeaways from this talk. The first takeaway is applications of the nanomaterials and why we have to. What is the first one is applications of the nanomaterials. And coming to the second point, the size matters. As nano is the smallest size, we know very well. We have got milli and micro levels also, millimeter and micrometer. We did not study the milli technology, and we did not study the micro technology, and we directly jumped into the nanotechnology. What made us to do that? That is the second part you need to understand. And coming to the third part, whether nanotechnology is it new or old? If it is old, why we are studying now? This is another part you need to understand. And coming to the next part, I will be talking about sensors, especially in the sensors also. I'll be focusing on gas sensors. I don't think that because it's all mechanical background, I don't talk much on glucose sensing, but I will be concentrating on sensors. In the meantime, if any questions are there, rather than coming here and disturbing, you please post in the chat box so that the coordinator can see and one person can ask me the questions so that we can have some basic discussions. If you see here, the applications of the nanoparticles, starting with textile, biomedical, healthcare, food and agriculture, industrial, electronics, environment, and renewable energy. This is the base code of the applications of the nanoparticles. You may be wondering, what are the textile applications? Once again, there are n number of textile applications like technical textiles. Textiles means like if you are working in a polluted company, polluted area, so that your cloth will be coated with some of the nanomaterials where whenever some dangerous gases are coming towards you, so that the gases will be disintegrated such that you will be saved. Kind of technical textile. Medical textile is another area where you, in the hospitals, the cloth whatever we use are antibacterial. Even the socks, the undergarments are kind of antibacterial cloths are available. And another interesting one is anti-strain textiles. So this anti-strain textiles are the one area where very interesting people are working in this area. This is one area where people are exploring. And then self-cleaning textiles, a kind of n number of electro-conducting textiles like it will be like this, where a soldiers or some persons, those who are working in an area where there is no electricity at that particular place, due to some small supercapacitor applications, the cloth will be coated with some of the conducting material. So whenever you need a light or charging kind of thing, you can use it, kind of applications. So there are n number of textile applications are possible with the help of the nanoparticles. And coming to the biomedical, it's a vast area once again, because it starts with drug controlled release. The drug controlled release means, like, let us say a particular person need to take some 7 to 8 tablets in the whole day, let us morning 8 o'clock, 9 o'clock, 10 o'clock, 11 o'clock, like that. Then the person, the particular tablet will be coated with some of the nanopolymer coated materials, such that after particular time, the polymer will disintegrate inside the body, so that drug will be released in a particular time. Kind of applications, like you can take all the tablets, but based on your time, the polymer might be coated on that particular tablet, such that it will be used. And similarly, biocomposites and wound dressing kind of thing, dental ceramics. Another area is biomarkers. Biomarkers is the one area now people are working very heavily. Why? Because as on today, biomarker and imaging of the cells. Like as on today, the technologies, whatever is there, let us take in a simple example, carcinoma or cancer patient. If you go to hospital, generally they do the topmost PET scanning, PET, positron emission tomography, where a patient could, in the patient, we can understand each one-day cancer cell also could be recognized. But the problem is what type of cancer cell it is. The meaning of that is proteins are nothing but amino acids, combination of amino acids which are there in our body, and each protein will have a different formulae, like different formulae, so that which type of protein is encouraging to grow carcinoma. If they know that, then for that particular protein, doctor can give medicine, kind of imaging. This is one where gold nanoparticles and silver nanoparticles, quantum dots, where people are using. Based on this, people could do an effective diagnosis process. It is called imaging and diagnosis as well as treatment. At a time, these all the things will happen. They're called therapeutics, MRI and hyperthermic. These are all some of the interesting areas where medical applications are coming up. And then food and agriculture is another area where lot of applications are coming up with the nanotechnology, like seed germination, faster growing of seeds, and pesticides could be used. Nanopesticides, where a less amount of pesticides could be used to more actively a kind of application. Industrial electronics, I need not talk much. An interesting thing is quantum computing. A quantum computer is the one where you can design a computer. As we know, the classical computer, what all we are working, laptops and other things, binary, 0-1 combinations. But if classical computer comes into reality, then 0, 1, and combination of 0, 1 and 1, 0. That means total 1, 2, 3, 4. These are 4 possibilities are there. Now we have a 0 and 1 binary systems are there. If this comes into reality, then what all the computers, the personal computer size is going to be decreased very, very small. There's a RAM size is going to come. These are all some of the interesting and fascinating applications. You may be asking a question. You may ask a question, why, sir, why you are telling so much about nanotechnology? What is the problem? Why we could not see the lot of products which are available in the nano-related products? This is a big question. At the end of the talk, you need to get answer for this question. Why we are unable to produce some of the nano-related products? What is the problem? Why we are unable to produce the nano-related applications in a very good manner? What is the reason? We will have a discussion in the continuous session in the next part of the talk, actually. So these are all some of the interesting applications of the nanomaterials. And you may ask a basic question: why nano? Why small? Advantage of small. Advantages of small is a simple question. If I ask you, if you have a sugar powder and a sugar cube, which one will mix very fast? If I ask you, then you immediately tell that sugar powder. Why? Because smaller can become more reactive. This is the interesting point. When the material is small, then the reactivity of the material is going to be enormously increases. But immediately you should also ask another question: why not milli 10 to the power of -3 meters, 10 to the power of -6 meters are not active? Why only 10 to the power of -9 nanotechnology? Why not milli and microtechnology? We did not worry much about it. What made us very fascinated about the nano 10 to the power of -9 need to be understood. Smallness is going to lead to a different properties, starting with the color of the material. So when you reduce the size of the material, the color of the material is going to be modified. As an example, if you take gold, normal color, everyone, we know the color of the gold. No one needs to tell us. Being an Indian, we know the gold color very well. So, but when you reduce the size of the gold to 30 to 40 nanometers, the gold color is going to become red, brick red. And when you reduce some more little, like 10 to 50 nanometers, then it will become blue in color. So because this is the peculiar property of especially gold. In case of gold, if you reduce the size of the color, if you reduce the size of the material, the color is going to be modified. Some of the materials, melting point. Another very interesting property is the strength. When you reduce the size, you know very well, being a mechanical engineer, grain boundaries are going to be modified. And because of the grain boundary modifications and other properties, the strength of the material is going to be modified. and conductivity. If I say conductivity, then reactivity versus current, voltage, all these electrical properties. So I can broadly say optical properties, mechanical properties, and electrical properties are chemical properties. Reactivity is the chemical property. So all these properties are going to be modified when you reduce the sum of these particular materials. And another interesting phenomena, if you consider in the case of magnetic properties, let us take a simple example. If you know antiferromagnetic material, if you remember, the antiferromagnetic materials, net magnetization will be 0. That means the total magnetization will be 0. Why? Because the spins in the antiferromagnetic will be equal and up and down. So what happens when I reduce the size of the antiferromagnetic materials to nano level? What happens is the net magnetization is not equal to 0. Why? Because the spins which are there, when you are reducing the size, they may break or they may do some modification. Because of that, you are going to have a net magnetization. That means, what I mean to say, same material whose fundamental properties are going to be modified when you reduce the size of the materials to a particular level. So what particular level is another very important point we need to understand. So here, the basic point what I am telling you is, when you reduce the size of the materials, their optical, mechanical, physical, chemical, electrical, and magnetical properties are going to be modified. Being a technological person, we need to tap that particular property and tailor for your application. Whatever application you are working, let us say you want to work a strong material, then you have to tap that particular property. If you are working on mechanical, like if you are working on optical property, you tap that particular material and use for your application and use it as per your requirement. You need to work on these properties of these materials. So if I now go to a very simple things, and I will try to explain what happens when the size of the material is reducing to 100 nanometers. Take a simple example of a spherical particle. So what is the volume of the spherical particle? Formula: volume is equal to 4/3 pi r cube. I told the diameter of the particle is 100 nanometers. Then I substitute it and I found the volume of this. Why I am telling it to you, in the next slide you will understand very clearly. And similarly, the surface area. What is the formula for surface area of a sphere is 4 pi r square. So if I calculate the same thing, surface area. Now, if I calculate surface to volume ratio, if I calculate surface area to volume ratio, it is going to be an abnormal value, 10 to the power of plus 7. But if I consider 1 meter, otherwise 100 meters, and use the same formula, you wonder the surface to volume ratio will be very small. If I consider 100 centimeters, the same thing will happen. So what I mean to say here is, if you take the surface to volume ratio is going to increase in the case of nanomaterials. Why? Because the surface volume is going to be this minus here. Here, because of this particular number 10 to the power of minus 9, and here also 10 to the power of minus 9, at these levels, it is a square, area is a square, volume is cube, so that what happens is the surface to volume ratio is enormously increasing. Even you cannot expect it. Similarly, if you consider the same in the case of meters and centimeters, that will not happen. So what I am going to tell you, my intention here is, when you reduce the material when you reduce the material to nano size, then at that particular point, surface area to volume ratio increases. So does the percentage of atoms at the surface, and surface forces becomes more dominant. This is the one peculiar thing which will happen in the case of nano, and which will not happen in the case of micro and milli. And when you reduce, yeah.
Oh, sorry, sir. Sorry. Actually, your presentation screen is missing, sir. Please kindly.
Someone might have.
Yeah, sir. We removed him, sir. Please, kindly.
Sir, I request all the participants, please pin the resource person presentation. You will get the perfect. I request all the participants, please pin resource person presentation. You will get perfectly. Sir, it is working perfect, sir. Please continue, sir. Sorry to disturb you.
No problem. No problem. Yeah. So here what I am trying to tell you all is, when you are in the range of nanometer, then the surface to volume ratio is going to play very, very important role, because the surface to volume ratio is increasing extraordinarily when compared to in case of milli and micro. As the surface to volume ratio is increasing, most of the atoms and molecules are coming onto the surface, and hence the surface energy of that particular material is going to be predominantly increased, and hence whatever property of that particular material might have got, that is coming to a very interesting phenomenon. These properties change nanoscale. That is the beauty you need to understand here. This is the first takeaway you need to remember very well. The first takeaway, what I am trying to tell you is, surface to volume ratio increases in the case of nanomaterials, whereas in the case of micro and milli, it may increase, but not this much. This is going to play very, very important role in the materials. This is the first takeaway of my talk. Once again, I'm repeating, the surface to volume ratio is predominantly going to be increases. Unknowingly also, if you say some materials property is different, one first answer is surface to volume ratio increases. That is the basic thing you should remember. Another example I want to give you, consider a cube. If you have a time, you can solve it afterwards also. You take a cube, you know the surface area formula for a cube. 6 faces will be there, 6 into length into breadth. So if you go on cutting into pieces into nano level, then you can surprise, it will cover almost a football ground. Very big ground could be covered with a small 1 centimeter by 1 centimeter cube material. So what I mean to say, when you are reducing the size of the material, the surface to volume ratio predominantly is going to be increases. Because of that, the chemical reactivity, the energy of the particles, the domains, they are going to have high energy. And because of that, the material is going to have a very different property what you are expecting. Another very important thing, you need not understand all these terminologies, but however, there is one term called quantum confinement. You know very well, all the Newtonian mechanics will work very perfectly with big bodies and small velocities. If I consider an electron, a proton, a neutron kind of things, then the Newtonian mechanics, whatever Newton's first law, second law kind of things, will not hold very good because of their different properties and phenomena. So based on quantum mechanical way, if you draw a graph, this is another very important graph you need to understand more effectively. Let us consider if I am drawing a graph, surface to volume ratio here on the y-axis, on the x-axis size of the particle, otherwise I can say diameter of the particle. So in the nanometer scale, what I mean to say, 10 to the power of -9 means 1 meter. Am I right? This is 1 meter, and this is millimeter, and this is micrometer. See here, when I am drawing surface to volume ratio, a graph from meter to, you see very clearly, till before 100 nanometers, it is on the x-axis. What I mean to say is surface to volume ratio is 1:1 only. It is not changing. You understood very clearly. So if you take the same formula, let us say take a cube, you take the same formula, surface to volume ratio, you can apply it and you can check it very clearly. It will tell you that till here, nothing is happening. Surface to volume ratio is remaining same. After that, interestingly, an interesting phenomena is happening. What is that? Is there is a increase in the surface to volume ratio. Are you able to see this very clearly? That means 1 to 100 nanometer. After 100 nanometers to 1 nanometer, something interesting phenomena is happening. What is the interesting phenomena? The phenomena is the surface to volume ratio is slowly increasing. This is a very interesting phenomena, and for this region is called a nanomaterial. So if a material whose size is in the range of 1 to 100 to 1 nanometers, we will say nanomaterial. In the any dimension, it may be, if it is a 3-dimensional material, if it is 1 dimension, let us say 1 meter wire, the diameter is 20 nanometers, then even we can say that is a nanomaterial. You understand, I assume. So here, basic thing is surface to volume ratio is going to be predominantly modified in the range of nanometer. If I say nanomaterial, its surface to volume ratio is more. If it is a milli, even though it might have got some different properties, but the surface to volume ratio area remains constant. That you need to understand very clearly. In the milli and micro, that is the reason we did not too much worried about milli and micro technologies, and we jumped into nanotechnology. So this is the first takeaway of my, that means first takeaway implication of my point. What I told you in the beginning, surface to volume ratio increases in the nanomaterials. That is the first point I told you. And I took an example and I gave you a graph very clearly, which shows that surface to volume ratio increases in the nanomaterials. And because of that, the materials will show a different properties, maybe optical, mechanical, electrical, and then chemical. This kind of properties are going to be modified based on your application. You need to tap that application and you need to tailor it and you need to use that particular material for your application. This is the first takeaway. However, don't worry about this particular point, but for the sake of completion, let us take, I told you when small materials are there, when size is small, like electron, proton, neutron, as Newtonian mechanics don't work, for them quantum mechanical phenomena will be used, Schrodinger wave equation, and the energy levels will be drawn. If I take same bulk material, the energy levels will be like this. If I take the nanomaterials, the energy levels are like this. That means more clear and more broad energy levels will be there. But don't worry at this point of time to understand this particular concept. Just leave it. So here, the first point, till now, what I was trying to tell you is nanomaterials will have the surface to volume, more surface to volume ratio, and milli and micro, that will not happen. And because of that, we were studying about the nanotechnology. technology. And coming to the next point, my next aspect is whether nano is new or old, or nano is something great. We need to understand some extraordinary things. It is not at all required. What all the fundamentals we know, what all the basic things we know, from there only we have to understand the nanotechnology. And you may ask a question immediately, sir, why, if that is the case, it is old. Even our grandmothers know how to prepare nano carbon tubes. May not be exactly nano, but micro kind of things. Like they know how to prepare kajal. Like for eye, they keep black color thing. Which one is in the homes, earlier days in the homes, they prepare with some chemical combustion reaction. They add some cotton and then oil, and then they collect the fog and they prepare things. So if you zoom it and zoom it and zoom it, you see very clearly these things will happen. And one more very important thing is, why nano now? If it is nano there, why people were not studied much? The reason is optical electronic imaging. That means earlier we used to have an optical imaging. Optical imaging is like microscopies, whatever microscopies we have. Maximum microscopy, what we could see is 10 to the power of -6 meters only. That means micrometer level only we could see. But when electron imaging came, electron imaging means like transmission electron microscopy, scanning electron microscopy, atomic force microscopy, kind of microscopies came, such that you could see atom by atom and molecule by molecule. From there, people were trying to understand more concepts, and because of that, more of nano we were studying actually. Even we know that the silver, now people, so much of people are talking about, as you know very well, as on this pandemic situations, people were telling that their surface cleaners are having nano silver particles. But we know in the olden days also, we know very well, our babies were started feeding with the silver cup and silver spoon. The basic reason is silver is an antibacterial material. So sometimes if you are not cleaning it very properly also, bacteria will not grow inside, and hence baby will not get any diseases. So the required amount of silver will be antibacterial, like silver coated undergarments are coming up in the markets already. So these are all some of the interesting applications are there, which are coming from basic understanding of the science. So let me take a simple example. If you see the peacock feather, whenever you see the peacocks, we feel very happy. And why? Because the colors, the peacock feathers have got very interesting colors. And when sunlight falls on it also, you see a different kind of colors. And the beauty is no one is cleaning them. In spite, they are very, very colorful and they look very bright in nature. So what made them? What made them such kind of things? So you know our basic physics and our basic chemistry, with that you could explain some concepts. But however, if I take a zoom, if I take in a microscope, a normal camera, if you take, you have a cell phone, and then if you go on zoom it and zoom it, you could see this kind of colors and this kind of brightness. But if I go to an electronic imaging thing, and then little more, then I could see a kind of things, very interesting morphology. This is the new terminology which is coming up, because when you zoom it and zoom it and zoom it, when you zoom it and afterwards, if you once again zoom it, it is like this: nano size holes repeated as a pattern on the nano scale. You see very clearly here, there's a small nano holes and a repeated pattern is happening here. So if you can design, if you can reproduce such kind of, see here, this is 10 micrometer, this is 500 nanometer scale, this is 100 micrometer scale. You see very clearly when you are visualizing slowly, when you are zooming it, the things are changing very differently. And you see this, and these both are okay. And after coming here, this is also okay. And once again, if I zoom this part, I'm getting a kind of very interesting nano size holes repeated as a pattern on the nanoscale. So whatever the fundamentals you know, use that fundamentals as well. If you can prepare this kind of a patterning, then it may be possible to come up with this kind of texture and this kind of structure, this kind of cloth or this kind of material or this kind of, so let us say as a simple example, if I can prepare this kind of paint and I can use it for my car, so that when I'm going, so people say that I want red car, I want blue car, I want yellow car, I want white car kind of thing. So depending on the light, your car shade will be changes, and it's a self-cleaning. You need not pay to a security or watchman who is cleaning, or you yourself need to clean it. No, so you need not do that, because it shows in one day you will get 5-6 colors. It's very interesting. Am I right or not? So the basic point what I am trying to tell you is whatever technology is coming up, whatever science is coming up, it's all from the nature. That is why being an engineer, being a technologist, being a scientist, we need to have a very sensitive eye towards the nature. I will give you another simple example. Only one boy came and told that apple is falling due to gravity. Why? Before also apple fallen, after also apple is falling every day. Every day fruits are falling down. But only one boy came and derived a formula, capital G, small g, gravitational constant, gravitational force, and everything. The basic thing here is we need to have everything, whatever innovations are coming, innovations are coming from nature only. This is what we need to understand. Another example, similarly, peacock, butterfly feather. See here, every butterfly is unique. Everything is very interesting. Every color is interesting. Every pattern is interesting. Once again, if I go on zooming it, it has got another very interesting pattern, a kind of a jip kind of patterning, like a jip kind of thing, which is a wings or cross sections of wings are having an interesting kind of patterning kind of things. And similarly, some of these things are having this kind of patterns. So what I mean to say, whatever you are looking with your eye is entirely different when you go to nanoscale range. It's a scale, it's the size. When you are reducing the things, they are looking in a very different way. And if you could mimic it, or if you could redesign it, and that is going to be the great innovations will happen from there actually. So from these concepts, people are coming up with security codes and credit cards, and then different types of photo identifications are possible with this help of kind of things. Another thing we see where from our childhood, we see lotus leaves. Lotus leaves will have when it falls on water, generally it will not touch because of hydrophobic nature. Simply we can say the contact angle between the material and this kind of this thing. So if I once again zoom it, you could see very clearly a different type of rods which are there, where it is giving a different feeling. Like if you, so what I mean to say here is the microscopy, like electron microscopy made everything very interesting, and everything, whatever we are thinking natural is this, but naturally is happening at the low levels is this actually. So you need to understand the differences, and then you have to, then innovations will come out. As an example, you can take simple examples like fogless glasses, fog-free glasses, fog-free mirrors are coming up. Already in the market, this type of TiO2 coated glasses are available, where water will not touch because of the hydrophobic nature of the materials. Similarly, if you take another example, kind of lizards kind of things which will walk on the floor or the walls, if I go on zoom it, size-wise, 75 micrometer, 100 micrometers, 10, 5 kind of thing. When you are going it's like a different kind of building blocks, exactly formed building blocks. And from there, these are all things. So basically what I want to say is technology or science or nanotechnology, whatever it might be, they're all for understanding the nature. So being a person of scientific person, we need to have a kind of scientific eye. That is what I want to tell you in the second part of my talk. So Here, the reflection point is, I was trying to tell you in the beginning that nanomaterials have got a lot of applications. And coming to the second point, surface to volume ratio is going to play a very important role. And nilly and micro materials might have got very good properties, but when come to the nano level, the surface area from after 100 nanometers, the surface to volume ratio is going to be modified. And because of that, the material is going to have a peculiar properties. And nano is not at all a new kind of thing. In spite, because of electron microscopies were invented laterly, people could see atom by atom and molecule by molecule. And whatever we do, it's all trying to understand the nature. This is what till now. And coming to the next part is sensors. Any questions are there? The concerned person can ask me, so that one person like a coordinator can tell me if something is there. Then I will move on. Otherwise, I will move on.
Yes, sir. Yes, sir. Sir, we will take at the end, sir, Q&A session. Now,
okay.
We can proceed, sir, please.
Okay. Okay. Thank you. Thank you very much. So being I'm trying to go a little slowly. Why? Because I'm a materials person. You are all a mechanical engineers. The group is mechanical engineers. So that is the reason I was trying to go in a very little slow manner. If you have anything, you can stop me at any point of time. So the next topic is sensors. In this sensors also, my broad area is gas sensing. Gas sensing means different, like you know very well, alcohol breath analyzer is one best example of a gas sensor. Basically, it's like LPG sensing. I work on LPG sensing, carbon monoxide sensing, nitrogen gas sensing. The whole setup is with me. So I will just try to explain what all from basic to the experimental part, and then some of my scholars' research work also I will show it to you. So if you have any questions, you can just. A generation ago, the word sensor was not widely used. Today, however, sensors are becoming found everywhere in our daily lives. Our world is changing rapidly, and sensors play an important role in this process. As an example, you know very well, taste, hearing, seeing, smell, touch, all these are the sensing organs we know very well. So these are all sensing organs, but they are not quantitatively, we cannot sense them. Let us say some sound is coming. So I cannot say how many decibels are coming. I can say louder or smaller. I can say bad smell or good smell. I can say I'm unable to get oxygen. That much I can say, but I can't say quantify that values being a human being. So for that reason, we need to have a lot of sensors. Generally, this is a task, and earlier in the olden days, it was a big task. Why? Because people used to take something and they go to the lab and they test it, and after that they'll get results, and people say that he drunk it or not. But as on today, you know very well, in the Hyderabad roads, if you see on Friday and Saturday, most of the police people will be there with, especially with alcohol breath analyzers. Basically, what they do, they will have alcohol breath analyzer. Then they analyze the breath, and based on that, there will be some reaction will happen. Based on that, they could see a number, particular number. Analytically, they could see a particular digital number. Based on that, they assume that they can come to a conclusion that immediately they can come to a conclusion that you're drunk or not drunk. This is what as on today applications. So the sensors are starting from environmental monitoring. And environmental monitoring is the one area where people are using lot of sensors. I may not exactly say in India, but even in India, people are using, I will tell you, like water, like in ponds, in the rivers, people keep some particular sensors. If something is wrong, if something is the levels are increasing, then it will indicate immediately. Let us say architectural, old ancient buildings also were covered with sensors like Charminar, Taj Mahal kind of things. They coat with some particular materials. If they are changing their color or if there is some modification in that, people could assume that something is wrong and they take necessary precautions. Coming to the medical, continuous monitoring is the one area where people are striving and struggling to do that. Let us take a simple example. If a person is a diabetic, you know very well, if you can know the exact value, whether the levels are low, levels are high, depending on that, the person could eat it or the person could take medication very properly. So what I mean to say, a continuous monitoring of particular diseases are very, very important. So this is possible with the help of a kind of sensors. So being a mechanical engineer, automobile field, I need not talk anything because there are n number of applications starting with balloons, accident, when pressure, basic point is pressure of balloons, and then a lot of other things are there, and manufacturing industry, and then defense industry, space, and then security, like a security. There are n number of sensors people are using it as on today. So just give me 1 minute. Sorry, are you able to see me?
Yes, sir. Yes. Yes,
Yeah,
yes, sir.
Thank you. Yeah, I just want to show a small video.
In 2017, Volvo Cars will put 100 self-driving cars on the streets of Gothenburg in Sweden, with real customers in the driver's seat. The unique Drive Me project is a part of Volvo Cars' journey towards a crash-free future. Volvo has now designed a complete system solution. Multiple radars, cameras, a laser, and ultrasonic sensors monitor the complete 360 view of the surroundings. A network of computers processes the information, high-performance GPS, and a cloud-based 3D digital map, continuously updated with real-time changes in the traffic environment. If anything fails, there is a backup solution, just like in an aeroplane. This includes vital components such as computers, sensors, steering, and brakes. On the road, the car is able to handle even the most complicated scenarios. The technology is so reliable that the driver can focus on something else without having to pay attention to the traffic. Just like good drivers, potentially critical situations are approached with sensible caution. And in an emergency, the car reacts faster than most humans. When autonomous driving is no longer available due to exceptional weather situations, technical malfunction, or reaching the end of the route, the driver is prompted to take over again. If the driver doesn't take over in time, the car will bring itself to a safe stop. With the Drive Me project, Volvo enters uncharted territory in the field of self-driving cars. Taking the final step to driving safely in real traffic with ordinary people behind the wheel has never been done before. And for drivers, the everyday commute transforms from lost time to quality time, open for work or pleasure. The choice is entirely yours.
So here, luxury driverless cars with embedded sensors. So why I have shown this video is, here, are you able to listen me?
Yes, sir, please.
Thank you. Thank you very much. So here, the basic thing is they use sound, they use light, they use space, GPS, they use pressure. They almost all the physical phenomena were used to develop a car, a manless car, basically. So my point of interest here is physical phenomena. Physical phenomena are like what I mean to say here is every aspect of physical phenomena were involved in this particular system, and hence here light switches, refrigerators, climate control applications, toaster. Even toaster will have a kind of sensor where people will be using. They're fond of most toys even today as an interactive toys also. So entering into a departmental store with automatical doors, even these are all possible things like giving a barcode to a particular person, even attendance kind of things, monitoring parameters such as the oil pressure, temperature, altitude, fuel levels. There are some of the things which are most of the times are based on sensors. So let me explain basically what is a sensor. Sensor is a converter that measures a physical quantity and converts it into a signal which can be read by an observer or by an instrument. What I mean to say, let us say we hear sound and we could say louder or smaller, or we can say reasonable sound. But if you have a mission which measures the sound, it will clearly gives the number, how many decibels of sound is coming out, a kind of, let us say pressure, like it is a mechanical sound waves. It is a sound wave, which is a mechanical wave. And if it is an optical related, optical waves, fiber optics kind of sensors, where there are n number of fiber optical sensors are available. So these are all different types of sensors. However, the fundamentals of the sensor, basic sensor is like this. A sensor is a combination of sensor plus actuator. These are the two things. But however, in the middle, the possibility is mechanical energy, electrical energy, even I can say chemical energy also. Are the phenomena that will happen, the physical phenomena that will happen. Based on this physical phenomena, I may be measuring velocity, I may be measuring acceleration, I may be measuring pressure, force, temperature, and pressure. So, depending on the physical phenomena, some measurable value I have to measure. In the case of electrical, otherwise chemical, I may measure current, I may measure voltage. If I measure current and voltage, I can measure resistance, I can measure capacitance, inductance, and conductivity. These are all the possible values which we can measure. Let me put it as a simple example. Thermometer. Basically, thermometer is nothing but its volume differences. Based on the temperature, volume increases or decreases. Based on that, we will measure this. We go to hospitals and people do ultrasound. It's a mechanical, it's a sound-based biosensor, basically. We can say sound-based biosensor. There also, in biosensor also, one particular bio-related part will be there, and similarly, actuator will be there, and a kind of things. So these are basically sensors are, once again, there are n number of types of sensors are there. However, requires a physical parameter, converts a sensor, acquires a physical parameter and converts into optical, electrical, mechanical signals, which are suitable for processing. Based on that, we will measure the value, and based on that, we could tell what value is exactly. This is the one of the very important takeaway from the talk. So basically what I am trying to tell here is nothing but any physical phenomena, like Doppler effect is a physical phenomena, otherwise photoelectric effect is a phenomena. From there, Ohm's law is a phenomena, Seebeck effect and Peltier effect. Thomson effect. All these are the different types of effects, physical phenomena where it is happening, and we will be measuring it and we will be quantifying it. Based on that, the sensor is going to work. And slowly, I was trying to explain sensor, and then, but my topic is gas sensor. My topic is gas sensor. So I will be going slowly into, I'm taking top down. I'm coming from slowly from top to down, like my gas sensing setup. So what is a gas sensor? Basically, we are sending some gas, whatever gas you want to measure. Let us say LPG gas or alcohol or some volatile gases. Even now we are working on biomarker gases. What is the meaning of biomarker gases? Means like alcohol breath analyzer, we are trying to develop a sensor for acetone and some other organic gases, where a sugar patient exhaled gases will have a different phenomena. Liver cancer patient will have a different exhaled gases. So if a patient goes to hospital, he need not do lot of tests. Basically, we have to keep one machine in his mouth and he has to exhale the gases, human exhale gas. Based on that, preliminarily, we can say that this man has got this type of disease. Kind of biomarkers are also will be coming up in soon. Actually, recently one RPS I got based on that human exhale gases, mainly for sugar patients. The exhale gases, a lot of acetone will be there, but also liver cancer patient will also have such kind of phenomena. But however, these are all the starting things where people can work this kind of areas. So gas sensing means not only outer side, but even as a biomarker also people can work in a different areas. So the basic idea of the gas sensors is like this. The gases are there, different gases are there, and because I'm a materials person, we prepare different types of nanomaterials and code on this, and we will send this to here. And here there are two possibilities are there. One is oxidization, other one is reduction, means giving electrons or taking electrons. These are the two possibilities are there for that particular gas. Whatever gas you are sending, there are two possibilities are there. One is taking electrons, another one is giving electrons. If it is taking electrons, something different will happen. There will be a interfacing electrical circuit, and then there will be detecting signal system will be there. And from there, you may measure current, you may measure resistance, you may measure voltage. If I measure current, I say it is an amperometric gas sensor. If I measure resistance in the circuit, that is called inductance, I say it's a chemoresistive gas sensor. If I say voltage, then I will say potentiometric gas sensing. You are differentiating it. Am I right or not? I was trying to tell you that here I can measure in the definition, I can measure voltage, I can measure current, I can measure capacitance, I can measure inductance, I can measure resistance, I can measure conductivity. If it is electrical related, if it is a mechanical related, then velocity, acceleration, force, pressure, and temperature. These are different things. However, so here the basic point what I am trying to tell you is a transducer will be there where it will convert the signal, and the signal is depending on the type of the energy, maybe electrical, maybe mechanical, maybe electromagnetic, chemical, any kind of thing. Depending on that, we will be measuring the output, and based on that, sensing phenomena will happen actually. I think this is very clear to you all. And you may ask my question, sir, already LPG sensors are available in the market. What is that? You are doing great. Yes, LPG sensors are available in the market, but they are at 90 degrees, means they need to give us a lot of energy. That means they are not at room temperature. LPG sensors are not at room temperature. we designed LPG sensors at 50 degrees. We were measuring all these values at 50 degrees centigrade. So that is what we patented 2 years back. We applied for the patent. So what is the basic thing is like whatever there, basically when you are doing research, you need to find the gaps in the research. Based on that, you have to continue your work. So in the olden days, when people are working on chemical sensors, especially nose and tongue, these are the things we can say chemical sensors. But olden days, people used to take one lamp. Mines, those who are working in the mines, they used to take one candle or lamp. After a particular time, if it is switched off, then they assume that sufficient oxygen is not there, we have to go back. After that, people started using birds. And when the bird goes inside and coming happily outside, then people think that, oh, it's fantastic, gas full of oxygen is there and people can go. But as on today, there are a new kind of technologies are coming up for gas sensing, and that is the basic thing. Here, a little bit of chemistry and other things will be coming up. You don't worry. The basic point I will be explaining you. The basic thing here is mechanism. How to design a sensor. If I say, so now what I am talking, I started with sensor, then I told with types of sensors, and slowly I moved to gas sensor. And after that, I told that there is a possibility of measuring voltage, there is a possibility of measuring current, there is a possibility of measuring resistance. So I have designed for my particular LPG, NO2, carbon monoxide, resistance-based setup. That means I will be measuring resistance. I will be measuring in my circuit resistance value after sending the gases. What all the types of gases I am sending it. So what happens? What type of material? Generally, materials or nanomaterials are of, we will take N-type. I need not explain N-type and P-type, I feel. You might be knowing the word N-type and P-type. So based on the materials, and there are different types of gases are there. Some gases are reducing gases, some gases are oxidizing gases. Reducing gases means electron donate. That means they donate electron to the material, whatever material is there we are using. For that, they donate the materials. Oxidization means they withdraw an electron. The electron withdrawing will happen here. So these are the two phenomena, oxidizing and reducing. And there are two possibilities are there, type of the materials, like N-type material and P-type material. So basic thing is, when material is here, when gas is coming here, so that it will oxidize or reduce, and based on that, based on the type of the material, the resistance may increase or decrease. May increase or decrease. So basically, if you are not understanding too much, don't worry. Basic thing is oxidization and reduction. Taking electron and giving electron. When gas is flowing onto the materials, it is the two phenomena which will happen basically. And here, another very important point is parameters. Parameters means, like being a materials person, I work on materials properties, especially the properties of sensing materials. Chemical composition, crystallographic structure, how crystalline it is, catalytic activity, surface structure. This is the property, especially I am interested. I told you, when nano-size materials, its morphology changes. The property of the structure, how it looks, the same material in the form of rod, same material in the form of flower, same material in the form of plate could be designed, could be synthesized using different phenomena, chemical phenomena. Specifically, I will be using chemical phenomena. And then parameters of the sensor. There are different parameters of the sensors are there, like thermal stability, selectivity of the gas response. What I mean to say selectivity, Let us say one person took coffee, another person took alcohol. The breath analyzer is showing coffee results as well as alcohol results. Some number is coming. Then it is not selective. It should only give values, some number for alcohol, not coffee. You understood the selectivity and the thermal stability, temperature-based stability, and gas sensitivity. Means like I will tell you like this. A Coca-Cola, a Thumbs Up might also have got a little amount of alcohol component, and even other high-end things also have got a high level. But if the gas sensitivity is not good, then it will not show the things kind. So it should be very, very sensitive. Then we can measure small values also. And operating temperature is the one area where we need to produce a lot of energy, like we need to use battery or we need to use current always, so that the temperature of that particular setup is going to be high. So as low operating temperature, that is the best one. And rate of response. What I mean to say rate of response is, let us take the top graph, sorry. If this graph, this is the time versus resistance I am measuring. I told you I am measuring resistance. I am sending the gas. So when I am sending the dry air and then particular gas, whatever, alcohol, LPG, whatever it is. So once I started, there may be possibility of increasing resistance or decreasing resistance. These are the two possibilities are there. Let us say in this case, the resistance is decreasing slowly. After a particular time, a saturation point comes. So before saturation and starting point is known as response time. And after saturation, once again, it will come to recovery time. It will recover to normal level. That means recovery time should be small, response time should also be small. What I mean to say, I can give you an example like this. A alcohol breath analyzer, I kept in one person's mouth. So it is going on, increasing the value. So it is not good. Am I right? It should be within 1 minute or 2 minutes, it should complete, at least seconds. How small is the response time? That much very good sensor it is. Let us say if I keep in one person's mouth and it is taking 20 minutes time. So he can't stay till 20 minutes. And it will look odd also. If I put, it should be within few seconds. If I am getting reading, the standard reading, slowly it will increase and go to a standard reading. Then that is the response time. And another person is there behind. And so I should get normal. Once again, it should come to 0. That is the recovery time. Recovery time should also come very fast. It should be fast. Otherwise, what happens? The second person will feel like how much time I have to wait kind of thing. So response and recovery time should be very, very small for a ideal sensor. So here, what I'm trying to tell you is in this slide, this is also one of the very important slide of the talk. Like I was trying to tell you, these are all the materials properties need to be understood. And these are the properties of the sensor also need to be understood. These are the two things we need to keep in our mind. So what are the parameters? Let us say if I say gas sensor, what are the different types of parameters we could measure, how to measure kind of thing. So what I told you, in this case, it is resistance is decreasing. I can take this or I can take this, anything I can take. So I took resistance increasing. So what happens here? This is going like this. And after that saturation came. This is the response time. And this is the recovery time. And sensitivity, if I say gas sensitivity, Ra minus Rg by Ra. What is Ra? Ra is with air. If I am not sending any gas, the resistivity. After sending the gas, Rg will be there and divided by, that is the sensitivity. And response time is another very important point. And recovery time and long-term stability. This is very, very important because this point is like after 1 month, after 2 months, after 3 months, after 4 months, after 5 months, after 6 months. Also, we need to test the same material. Based on that, we will say it's a good sensor, good gas sensor. So I was telling you that I'm working on chemoresistive gas sensor. What meaning of chemoresistive gas sensing? I will be measuring resistance in my circuit. This is the This is the resistance, like a multimeter kind of thing, a resistance. And I need to give some basic voltage for the circuit completion. This is the sensing probe, the material which I am preparing, and this is the gas coming up. And when gas is coming up, it will interact with this, and due to this, there may be oxidization or reduction will happen. Because of that, resistance may increase or may decrease. Based on that, we will calculate the values, and based on that, we can say it is a good sensor or what type of sensor it is, kind of things could be understood very clearly. So broadly, I can say there are 4 chances, 4 possibilities are there. One is N-type material, and the chance is reducing gas. If that is the case, conductivity increases. That means resistance decreases. In the other case, oxidizing gas, same N-type, then conductivity decreases. Inversely, the resistance increases. Another case is P-type, gas reduces, reducing gas you use, then it will be conductivity decreases. That means resistance increases. And similarly, oxidizing. These are the possibilities, 4 possibilities are there. That means what type of gas you are using and what type of material you are using. Based on that, this type of setup we can design. So when you are designing a particular sensor, you need to have a lot of things you need to take care. Like ideal gas sensor is characteristics are accuracy, respond rapidly. Respond rapidly is nothing but response time and recovery time should be very, very small. Be specific. That means it should be selective for that particular gas. That means if I design an alcohol breath analyzer, for everything it is showing some value means people don't accept it. Why? Because it is not selective. It is reacting for all the materials. Sensitivity should be very small, and operating temperature should be small, and size of sensor should be small. Maintenance cost should be small. Repeatability should be very good. Durability and eco-friendly. These are all the some of the ideal characteristic of a sensor. Okay, this is what the second part. So until here, the reflection point here is I was trying to tell from sensors. Slowly I came to gas sensors, and slowly I came to chemoresistive gas sensors. I told you what is the chemoresistive. I'm going to measure resistance in my circuit when I am sending the gases. This is what I was trying to tell you till now. And after here, this is 3 case studies I want to give you. And these case studies, why I want to give you these case studies are, this is an MTech student work which was published in very good impact factor, around 4 impact factor journal. And this is this is also published, and this paper also published. These are all like very simple works. People sometimes say that they need to have a lot of setup, they need to have a lot of equipment, then only we can do research kind of thing. These 2 are like MTech students research works, and this is a PhD scholar who is specially working on morphology. Like we designed the same material, 8 types, like different types of morphologies, and based on that we want to see how the sensing properties are going to be modified basically. So these are all very simple, very like you need not have very great equipments, but however for characterization and other things you need to approach some or other people. We use basically IEDs. IED means interdissociated electrodes. This type of different types of electrodes we purchase, and on the top of this, we will coat our nano material. Here we will coat our nano, whatever we prepared. And this is aluminum electrode. Here also we coated our nano material. These are flexible sensors. Here also we have a kind of coating setups will be there, and we coat our material here and we use for sensing setup. This is I have got a CRB project like in 2012 or 13 I got, and I have published on this instrument around 70 to 80 publications. the person who was introducing me, like he told that he took old biodata. I think there are around 300 publications for me, only international publications. So in this instrument itself, we have like around below some 50 publications are there. And here, this is a basic simple instrument actually. This is a kethylimeter where I can measure resistivity in the range of micro ohm modifications. That means I told you I'll be measuring resistance. Am I right? So when I am measuring the resistance, it is very small in the value. So it is in the range of micro ohm. That means 0.000000 changes also I could measure with this type of instrument. So what gas I want to measure? Let us say I want to do LPG. I will connect LPG gas here. If I want to measure carbon monoxide, I will connect carbon monoxide. If I want to measure NO2, I will connect there that. So depending on the gases, this is air gas, zero air. The zero air means in this chamber, normal air will be there. All other things will be there. So I want to evacuate that, and I want to add zero air. So that what happens is there, I will be getting ideal conditions. These are the flow meters where I can measure how much flow is coming. I can control ppm level flow changes, and I can mix here gases very properly. There will be a mixture will be there, and I can send the gases here. And then when gas is going there, and this IEDs are there, and this is a 4-probe setup. Generally, if I want to measure resistance accurately, I have a setup called 4-probe. There will be 4 probes will be there, and that I will be connecting. These are the connecting points actually. So I will insert this there actually inside, and I can increase the temperature approximately 150 degrees centigrade like that. And then here, this is basically a computer, and this is vacuum pump section. And here for LPG sensor, there is a problem. Normal regulator will be there. That regulator, you can't monitor how much gas is going or coming like that. So we designed our own setup based on Archimedes principle, simple setup where we can control the volume of the LPG gas, the only LPG gas. Other things like carbon monoxide, nitrogen, they have got their own meters will be there. They will show, because I am using normal household LPG sensor, LPG cylinder only here. That is the reason we set up this kind of things actually. Okay. So here, this is the setup how we in the lab we designed actually based on the literature, and with the help of VB Ceramics actually, they supported their Chennai based company actually. We designed this setup actually. So here, how to prepare SMO2, SM2O3, a simple method, a simple basic chemistry is required actually. So this is the abstract graphical figure. So we prepare this particular material, we characterize it, and then we coat on this electrode, and then this electrode will be kept in the circuit, whatever I shown here. This electrode will be kept here, and then allow the gas to go. Gas will be sent there, LPG especially, and then CO2 and the oxidization reduction phenomena will happen. There will be in the increase or decrease of resistance will be there. That I am going to measure, and that I will be plotting it in a different formats basically. That is the graphical image. So we used a very simple and economical method is called biotemplate hydrothermal synthesis. We took egg, normal egg, chicken egg only, and then we peeled off the shell, the core on that shell of that, and then this core actually. This is the core. After this, there will be a small kind of a polymer kind of thing will be there. Eggshell membrane we took it, and this membrane we did TEM, and it is like this, like a rod kind of different structures would be there, and that we used, and then we use different types of basic chemicals like SMO2 combination, and then we mixed it, and then basically we used hydrothermal synthesis. The meaning of hydrothermal synthesis is nothing but a kind of pressure controller, basically a pressure cooker. Basically, it's a simple pressure cooker. We will close the knobs fully very tight. It is a metallic bomb kind of thing. We will add all these chemicals inside, and we close it, and we will put it in the low temperatures, maybe 150 to 100 degrees centigrade for 40 hours, 30 hours, 20 hours, depending on the basic understanding of chemistry, how they are going to prepare the same material. Same material we can prepare like rods, we can prepare like different hierarchical structures, we can prepare like a plate, we can prepare like a flower kind of structure, and we want to study for a sensor application. Let me spend 2-3 minutes here, but it may be a tough task for you to understand, being a mechanical engineer. We do X-ray diffraction. It is one particular way of understanding the material's properties. Like we want to study whether the same material I prepared or not based on these particular peaks. Based on these particular peaks, we can tell that the same material is prepared. Some optical properties, like other things. I don't want to like I don't know, like, and this is the morphology. Basically, it's like a rice kind of structure, small rice kind of structure, small rod kind of things were prepared using the same method. And also, the same material we could prepare with some chemical small changes. Very big rods, small rods with a little more diameter, a kind of flower kind of structure, a kind of hierarchical structures, a kind of hierarchical structures, kind of a different kind of structures. So the same material, but morphology is changing based on some of the techniques, methods we use. And these materials we want to study for my application. What is the application? Gas sensor application. How we do that? We take the IED, that is interdissociated electrode, and then based on drop, it is called spin coating or drop coating method. Use this, put a drop here, let it dry, and then use these two knobs for connecting purpose and put it in the chamber here. So what we will be doing? First we will allow zero gas and then close it, and then allow LPG one by one, like 1 ppm, 2 ppm, 3 ppm, 4 ppm, like that we slowly increase. And based on that, how current is going, how resistance. I told you it's a 4-probe setup. 4-probe setup is there, how the resistance is going to be modified. And this is how we are going to get. So here I also added RGO. RGO is nothing but another material called reduced graphene oxide. And there I increased response versus LPG concentration. First I have to study. Once LPG concentration is fixed, then I will go time versus resistance. I increase the time, same ppms I continue. Like one threshold ppm I will measure, and then same ppm, and then I will measure this. After that, from each, if I take each one, any one of this figure, and then I can measure response time and recovery time, and from there other calculations I can do. And also, this is what I told you, selectivity. What I mean to say selectivity, it is like this, like other gases. I tried N2, I tried ethanol, acetone, NO2, CO2. There is a response, but very small response is there when compared to LPG. How much? 700 ppm, all 700 ppm at 27 degrees centigrade. This we have to do. So we did selectivity, we calculated response and recovery time, we calculated what is the threshold kind of thing, and from all these things, like this, we can calculate it. And here, what we did in this special work is we bending means because we want to use it for some other cloth application also. The same sensor could be kept in cloth, and how the results are going to come. Like different types of bending levels also we increased, and we studied that also, like how it is going to affect mainly in the case of bending kind of things. So these are different tabular values. Don't worry about all these values. But what I am trying to tell here is what all the published work and how we are comparing with the results kind of things. Basically, we'll be measuring sensitivity, selectivity, all other properties. It is one way of sensor property, gas sensor property. Similarly, another case study is CuO2. This is also similarly a kind of application. Different morphologies. Once again, you could see a different kind of morphology, and then we use the same materials for the application. Once again, we calculated almost similarly response time, recovery time, and then other things. It is also MgCuO2. This is another work where MgO is MgO and two types of materials we added here. And then, like once again, like basically we are concentrating on morphology-based studies. Means material and morphology, how it is changing with respect to the system. These are all some of the things. Here, we patented this also. Basically, we took bacteria. Sorry. We took bacteria, we took fungi, protein powder. From that, we have to extract some protein, and that protein powder, fungi powder, we added to the nanomaterials, whatever we prepared, and then we studied the sensing properties. It is interestingly, some of the interesting phenomena were happened here also. We could see that temperature reduction in the like lower temperature reduction. This is the images of bacteria, and then we collected bacteria protein, and then we did all scanning microscopy images, and then we added, we did X-ray diffraction to show that, and then this work actually we were doing, we were patented actually. So these are all some of the interesting results I got it. So here, till here, what I'm trying to tell you is, so first I was trying to tell you like what type of sensors, and then gas sensors, and then chemoresistive gas sensors, and then a type of different types of nanomaterial synthesis. Everyone can do with a normal, simple chemistry lab, small chemistry lab, and then based on that synthesized material need to be characterized, different characterized, and show that the material, whatever you imagine, you were thinking was prepared, and then use that material for application gas sensing in the 4-probe setup, whatever we design, and then measure some values, and then we can publish this kind of actually. This is what about the gas sensing setup. And the organizers, I have a glucose sensing also. Can I talk about sensing, glucose sensing? It will be.
Yes, sir. Sir, you can proceed, sir. No problem. Sir. We are having sufficient times. Yes, sir.
Thank you very much. Okay.
Yes.
So basically, glucose sensing. What is the glucose sensing? Means like in a human body, there will be some problem will be there, like glucose levels will be increasing or decreasing. So that measurement, monitoring of glucose levels is one of the very important aspect of a diabetic patient. Why? Because continuous monitoring is the one parameter where people need to do it in the case for the betterment of the diabetic patient. As of now, you know very well. There are number of in foreign countries, a lot of diabetic patients will be there. But being India is also economically growing, is becoming developing country as well. The diabetes are also increasing very effectively. The basic thing is the energy levels, the glucose distribution will not be very properly happen, and it will not go to proper organs. So sometimes it may be high or sometimes it may be low. These are the two possibilities will be there. So absorbed into bloodstream, and this bloodstream will make us have normalized glucose stored as a glycan in muscles and liver, and this will be absorbed by blood streams. But the problem is this absorption, like there are different, like internationally people know what is the values of levels of the glucose as how much we need to have, that I need not talk. But however, this is a normal glucose in the blood, and hyperglycemia and hyperglycemia. These are the two phenomena are there actually. So low and high glucose levels. Low is also problem as well. High is also problem. A normalized glucose levels need to maintain a diabetic patient. A normal person will glucose levels will be normal, but in case of a diabetic patient, this or that will happen. So if you can monitor the glucose levels, then the treating the person will be very effective, and it could be done very easily. So you know very well, as on today, due to the diabetic, there are a lot of side effect issues are coming, like respiratory issues, high blood pressure, cardiovascular diseases are coming up due to this particular diabetic thing. So to sense the diabetic, first of all, you need to understand what is a biosensor. Biosensor is nothing but is an analytical device which is used to determine presence of concentration of a specific substance in a biological environment. If I say there will be a bioreceptor and a transducer and a signal and display, normal sensor type only. But here, one separate thing is a bioreceptor. What I mean to say bioreceptor is, sometimes bioreceptor is nothing but a blood, sometimes bioreceptor is nothing but our body, sometimes antibodies, sometimes bacteria, sometimes cells, sometimes tissues. Depending on the type of the sensing phenomena, we need to use different type of bioreceptors. Like in the case of kind of, I will explain you. In the case like when you are doing biosensor, like enzymes, people can use enzymes, antibody, nucleic acids, bacteria, cell, tissue, organs. These are all some of the things where people will be using. Like the transducers are electrode and pH change. If you are, there is a pH change, we can measure something. There, if heat, temperature, body temperature, heat kind of thing, light. In imaging and some of the MRI, in MRI we will be using magnetic resonances, basically magnetic things, and electromagnetic radiations. Light is nothing but an electromagnetic radiation, and mass change. These are all the some of the signal transducers people will use to have, and then amplifiers will be there, and based on that your electrical signals will be there, and based on that we will measure the we will say that it is a biosensor. Basically, biosensor is a compact analytical device that uses specific biochemical reactions to detect and measure targeted compounds in the biological samples. The molecule recognition element include receptors, enzymes, antibodies, nucleic acids, microorganisms, and lecitins. These are all some of the things where people can use it. So now, if you see the glucose sensor, basically it's nothing but glucose will be there, and the glucose will once again here also the same phenomena. What I was trying to tell you, reduction and oxidization. These are the two phenomena will be there chemically. So when glucose reacts with some of the materials, it may oxidize or it may react. It is called glucose electrochemistry. In the beginning days, people used to measure H2O2, hydrogen peroxide concentration. Based on that, people used to say that the level of glucose levels of the particular patient. That used to be a very big instrument where people say that people used to determine the glucose levels. That is called generation 1, first generation glucose sensor. So I told you similarly, a little bit of electrochemistry is required, glucose chemistry is required. That means this is the formula for glucose. And don't worry, if you're not understanding, don't worry much. So glucose will oxidize or glucose will reduce. These are the two phenomena will be there. That's it. You need not worry too much about to understanding this thing. Basically, oxidization or reduction. These are the two phenomena will happen. Once again, we may be measuring resistance, we may be measuring current, we may be measuring current, we may be measuring conductivity, we may be measuring capacitance, we may be measuring voltage. If I am measuring voltage, then we will say voltammetric glucose sensor. If I am measuring resistance, I will say chemoresistive glucose sensor. If I measure current, amperometric glucose sensor. Like that, the sensors will be there. As I told you, these are the first generation where people started only H2O2 measurement. And then in the second level, people used some other materials, GOX material, where people tried to work on this. And in the third generation, for more accuracy, people started using enzymes also. A different enzyme. So now, when you go to hospitals, laboratory center, they pick the blood and they do this kind of test. This is a third generation test, but there is unfortunately there is a drawback, especially for some particular persons. The glucose levels will be very high or very low, but they look normal. There won't be any symptoms. That means the problem is the measurement. Because the enzyme is there, that particular enzyme is reacting, interfering in that particular person's, because it's depending on the type of the DNA, depending on the type of the person, there will be different enzymes will act differently. So sometimes there might be a problem. Unfortunately, despite the electrode nanostructures, only few enzymes are able to directly transfer electrons from their active sites to the electrode. Sometimes it will not happen. The phenomena will not happen. And due to that, you may be getting wrong results. That is one big problem in the case of the third generation glucose sensing. That is enzymatic glucose sensing. That is why we were doing non-enzymatic glucose sensing. That means in our sensing setup, we don't use any enzyme. We will use, without enzyme, we will be measuring the glucose. That is why it is called as non-enzymatic glucose sensing. Is it okay? And here we are measuring voltage, not the current. It is called voltammetric glucose sensing, basically. You know very well, but recently we applied an Indo-UK project with non-enzymatic glucose sensing. The comment was, it's a very old work. And I am thinking we are working on fourth generation. In spite, people are telling old. Why? Because as on today, there is a smart contact. It is like a sugar paid coming up kind of things, like continuous monitoring of glucose, like with saliva. Without pricking a person or without hurting a person, saliva could be taken from mouth. Otherwise, also sweating. You can keep somewhere the small instrument where the most sweating is coming. So that your glucose levels could be monitored very effectively, like a app in a small watch or in a cell phone, mobile kind of things, are possible in near future. If that is coming, continuous monitoring of glucose, then lot of problems will be solved. Because if low glucose levels are there, you can act accordingly. If high glucose levels are there, you can act accordingly, so that things could be in a better position actually. So here also, don't worry too much. I'll be talking much of kind of nano thing. So here, core and shell. It is nanoparticles will be different structures will be there, like they will be in different formats. But we were in this particular project, we were doing core and shell. That means inside the one material, outside another material. We synthesized this type of materials, core and shell kind of materials. Why? Because we want to control oxidization and reduction in the blood, and hence it will be very good. Results will be coming very good. Core shell nanoparticles. They are surface modification, ability to increase the functionality, stability will be very good. Mainly controlled release of the core. This is one core. Inside this will release controlly, and that is one. And here we have got our own. I told you we also work on some of the agriculture related stuff. We developed our own green synthesis material. We developed 4 to 5 types of tulasi. Tulasi is nothing but osimum, and which is like Krishna tulasi, Vana tulasi, Rama tulasi, kind of different types of tulasi flavored plants. And then with that plants we grown ourselves, and then we use the same material for the synthesis of this particular nanomaterials actually. And because of the contents, the chemical contents which are available in the tulasi, it will be useful in the synthesis process. We did a big synthesis process. Don't worry about that, all that. And then similarly, we were doing X-ray diffraction, FTIR, UV, and then blah, blah, all these things. And here you could see very clearly in TEM images, a core and shell kind of outside is different and inside is different. A kind of possibilities are there. These are all some of the nanoparticles which we prepare. Here, this is a separate instrument which we have in our lab. It is called cyclic voltammetry. Cyclic voltammetry is CV, capacitance versus voltage we will measure here. This is the setup actually. And here, from this, there will be 3 electrodes will be coming, and this is basically a liquid. We will be keeping some liquid inside, and then one electrode is reference electrode, one is a counter electrode, and one is the material whatever we prepared, we coat here in this particular carbon electrode. It is called screen printed electrode. It is a screen printed carbon electrode which we need to purchase it, and then we have to coat the nanomaterial in this particular place, and that we have to keep. And then we will be allowing different currents and voltages, and we can measure potential, we can measure current, we can measure the current difference. So I told you like very clearly, it's a potentiometric glucose sensing. I will be measuring here potential differences in the particular cycle. And we have got some collaborations with some of the hospitals. We take the blood, and from the blood we have to take the serum, and then we will be measuring with normal instruments, and we will be comparing this also, so that there will be a lot of difference. And here a lot of chemistry and electrochemistry will be involved, but basic thing is we will be measuring the glucose levels in the blood basically. And don't worry about all these results. These are all different results actually. And here also, like you can see here core and shell separately. This is the core and this is the shell. This is one PhD of one of the PhD student, and now he is in South Korea under B2K fellow. He moved to South Korea, and the person who designed, like who helped in designing gas sensing setup is Dr. Gautam. Now he is in University of Manchester, and he is working in the group of Nobel orator who got in 2015 Graphene Nobel Prize actually. So they are there. And generally when I give talk for our outside Telugu states, I will talk about JNTU, but you know very well about JNTU. I need not talk much about JNTU. But however, I work in an Institute of Science and Technology in one of the JNTU constituent college, which is in Kukatpalli JNTU main campus. Ours is not like an engineering college. We have different centers, like we run MTech and PhDs. We don't have undergraduate courses actually. So I work in Center for Nanoscience and Technology. Ours is Nanomission funded center, and we run MTech in nanotechnology, MS by research, and PhD in nanotechnology and nanomaterials. I told you the gas sensing work is done by one of the mechanical engineering BTech and MTech in nanotechnology student. Now he is moving to IIT Mumbai for his PhD in material science actually. So there are different branches students will be there actually. So I'll also be spending some of the time about my research, what all the research, what is happening at Center for Nanoscience and Technology. We work on energy applications. We work on graphene-based materials and perovskite solar cells and dye-synthesized solar cells in this area, graphene-based nanomaterials and battery applications. In the battery also, we work on lanthanum-based cathode battery material applications especially. This is one area we work on energy. And agriculture is like seed germination. Like we work on different types of seed germination, faster growing of seeds kind of things. We have a collaboration with seed department in agriculture university where we grow different types of things, and then we will like seed. We patented one work on corn seed, and then we also work on antibacterial activity and not antiviral. We are slowly working on that, and anti-cancer. Because my postdoctoral research is in Johns Hopkins, I worked on imaging of cancer cells, especially CXCR4, based on surface enhanced Raman spectroscopy. And then I also work on my basic work is on sensors. Once again, in the sensors, we work on biosensors like glucose sensor and volatile gas sensors, and also human breath analytical gas sensors. We work on gas sensors like LPG, NO2, carbon monoxide kind of things. We also work on humidity gas sensing setup. We have a humidity gas sensing setup also, like how much humidity is there in the atmosphere kind of work also we do. And then that is also one project. And then we also work on air pollution, water pollution, sorry, not air pollution, water pollution, especially absorption, chemical absorption phenomena. These are all like broad areas where we work based on materials applications. These are all some of the instruments which are available with us. TGDT, a thermogravimetry, atomic force microscopy, X-ray diffraction. Raman spectroscopy is not working as of now. We have UV spectrometer, ball milling, spin coating, thin film unit, spray pyrolysis, and then nanoparticle size analyzer, from where we can get the size of the particle, and chemical vapor deposition, cyclic altimetry, solar simulator, laminar air probe, and incubators, digital incubation. Like we have nanofluid ultrasonic interferometer. Basically, we work on thermal conductivity of different types of liquids, like engine oils. Especially we work on engine oils. Basically we add some of the nanomaterials, we resolve the sedimentation issues, and we want to improve the thermal properties based on KD2 probe we will use, and we work on thermal conductivity of this type of nanofluids. Some of the mechanical students and mechanical MTech project people are also worked with me in this kind of area. And we also work on contact angle. Basically this contact angle mission is one hydrophobic nature, like how the contact angle is modified, like different types of hydrophobic and hydrophilic nature materials could be used. Fourier transformation infrared instrument is there, which we can measure functional groups of the material. These are all some of our facilities which are available with our Center for Nanoscience and Technology. And we outsource also. We have a separate website in JNTU. If you go to JNTU, there Institute of Science and Technology, and there in Center for Nanoscience and Technology. From there you can. These are all some of the PhD people who completed PhD with me, and there are 14 PhDs were completed. All are full-time PhDs most of the times, and then at present I have 6 PhD students with me. Thank you very much. If any questions are there, very welcome. And shall I stop the screen sharing?
Yes, sir. Yes, sir. Thank you, sir. Thank you. This is very excellent presentation, sir. Now, shall we go with the question and answer, sir?
Yes, I'll be very happy to. If I know, I will try to answer. Otherwise, we'll have a discussion happily.
Okay, sir. Sir, I'm going questions from the chat box, sir, from the recent.
Okay, fantastic. Yeah, please.
Yes. One question from Professor Toshit Jain. Types of precautions and in vitro test to be conducted before the implement in living beings. Shall I repeat, sir?
Please repeat, sir. Please.
Types of precautions and in vitro test to be conducted before implement in living beings.
Yes, it is once again a big topic actually. We need to be very particular and very careful in vitro before we are going to do any in vitro test. But however, in these sensors, whatever we are doing, we don't do any in vitro studies. Only in cancer related things only we do in vitro and in vivo studies. At this point of time, we will be, because we are working on human exhaled gases. Basically, human exhaled gases are nothing but different types of organic volatile gases that we will be studying, sir. And in vitro studies and toxicology studies are entirely a different set of things, sir. Actually, we need to have a very wide things. We need to take care a lot, actually. And he might have asked that question due to I told. I am using a kind of seed germination kind of things. So when we are using seed germination, we use the nanomaterials which are good for health and minimum quantity. Let us take an example. If you take salt 1 kg, it will be very dangerous to health. You take only little amount of salt, then that will be very good. Similarly, the type of the materials, whatever we are using, we need to take care a lot.
Thank you, sir. This is another question from Professor Hemant. Dear sir, why are you using SM2O3 RGO composite for the sensor? Can we use the TiO2 to replace the RGO?
Yes. We can use TiO2 can be used. Already a lot of work is done on TiO2. SM2O3 is a new kind of material. Much of the people did not done that work. See, when we are working it actually, in the point of research, what we will be doing is, we will be literature survey we have to do, and based on the literature survey we will be selecting different types of materials. I told you this is an MTech project. Who did a MTech student? So in the process of literature survey, we felt that this material is less work is there, and we want to explore on that particular material. And basically our concentration is TiO2 can also be used. It is not wrong. It is nothing wrong in that actually.
Thank you, sir. This is another question from Professor Narayanan. Why we go for TEM, SEM, AFEM? What is the difference between these three in nanoparticles characterization?
A very good question, sir. Sir, generally, if you are taking SEM, scanning electron microscopy, the scanning electron microscopy is in the range of micrometer. Sometimes it may give in the range of nano, but it will be 500 nanometers, 1000 nanometers kind of things. So it is a little bigger materials. If you go to transmission electron microscopy, it is in the range of 10 nanometers, 5 nanometers, 6 nanometers, could also be studied in transmission electron microscopy. Another beautiful thing is, in the TEM, you can get electron diffraction pattern. Whereas in the case of X-ray diffraction pattern, electron diffraction pattern also could be achieved. So when compared to SEM, TEM is more effective. If these are the two things. If I am coming to AFM, atomic force microscopy, because in the case of TEM and SEM, you need to have a coatings on the particular material. Whereas in the case of atomic force microscopy, you need not coat anything on the materials. That you need not have any charged materials. Like a polymer, a living bacteria, or living anything could be used in atomic force microscopy. These are the three different ways of way of imaging the sense. Like in electron microscopy, in transmission electron microscopy, tunneling will happen and the very thin material need to be kept. In scanning electron microscopy, there's a scanning thing, it will scan and it will be different phenomena. In atomic force microscopy, it's basically F is directly proportional to like a spring constant formula, basically Kx. F is directly proportional to Kx. Kx is a spring constant, basic formula. It works on attractive forces and repulsive forces. Atomic force works on basically, you know the formula, F is equal to inversely proportional to 1 by R square. R is inversely proportional. But when they are come very, very closer, a repulsive force comes into reality, and that is going to play a very important role. And based on that, there will be a tip and other phenomena will be there. These are the three different techniques. Depending on the technique, we have to work actually. I think I gave you basic concept actually.
Yes, sir. Thank you, sir. This is another question from Professor Rajanikanth. Can we use electrode deposition method for this morphology? The morphology, I think, while you are speaking with morphology, he has asked the question that time, it seems.
No problem, sir. Yeah, you can use different types of techniques to synthesize different materials. It's all like your application. What are you looking for, and what do you want to do? It's all depending on method. There are different types of synthesis methods are there. Simply you can mill it, ball mill, and use that material, or you can do electrodeposition. You can do any number of things. You can do it actually. It may be possible actually. We never tried. It may be possible.
Thank you, sir. This is another question from Professor Hammond. Dear sir, size of SM203 you had prepared.
The size, okay. So it is in the range of nano, sir. I don't remember exact size value, but crystallite size is also below 100 nanometers, and approximately they are in the nano range. I exactly don't remember the number.
Okay. Thank you, sir. This is another question from Sunil Kumar. Suppose there is a need of coating of nanomaterials in electrode, then how it is possible?
So there are different types of coating methods are there, dip coating and blade cut coating kind of. There are n number of literature methods are there. So once again here, you need to see addition and how the material contact and all other informations are very, like you need to be very careful when you are coating it. Based on your requirement, you have to select the coating methodologies actually. We cannot say broadly, this method is good or this method is not good. And one more very important thing I want to have an answer here. See, this much of nanotechnology I told, and process engineering is a very big problem. I can prepare 1 gram or 2 gram or 10 grams of material with the same morphology. If I go for 250 grams or 1 kg, then it will be a tough task. I may not prepare same morphology and same kind of thing. This is the tough task as on today because of chemical engineering. Process engineering is required for this kind of materials. Not in the case of bulk materials, it will be very easy to prepare. Let us say if I ask you to prepare 1 kg, I can prepare, but with the same morphology preparation is going to be a tough task actually. You have to do a process engineering that is a tough task actually. That is what people are trying to understand and people are trying to develop it actually.
Thank you, sir. This is another question from Professor Sunil Kumar. If the nanomaterials is found to be crystalline in nature, what is the advantage of that?
The question is not very clear, but what I understand is nanomaterials might be crystallite, might be amorphous material also, sometimes nanomaterial. Crystallite is, anisotropic properties. That means when you are sending temperature or light, it is going inside the material. If it is a crystal, it will take its own direction. Whereas in the case of normal material, it will not be. So once again, like if you are working with polymer, a different application, nanomaterial, it's a crystal, it is a different application. So once again, like it's all like once again depending on your application, what is that you are looking. If it is a crystal, oxidization things, other things will happen. It's all like different things, sir, actually.
Thank you, sir. This is another question from Muralidhar Singh. How to check the adhesion of the coatings?
Adhesion of coating is there are different phenomena are there. We do some of the work on we are working now with BHEL R&D with corrosion kind of things. So there we are using different phenomena for adhesion. Like we will be using some polymer, we will be using some glass material, we will be using some coating on that. So that coating setting is a different setup actually. Coatings itself is a different area where people work. Scratch is the one simple thing people do, and there are acid treatment, base treatment kind of things are there, bleach treatment kind of things will be there. So there are different things based on that people will work.
Thank you, sir. This is another question from Professor Oblesh. Sir, give the practical applications of nanosensors and microsensors.
I did not get the question exactly.
I will repeat, sir. Sir, give the practical applications of nanosensors and microsensors.
Okay. So let us take, now we saw that car, there are n number of sensors are there. They might be micro. What I mean to say nano or micro, if you are using some material whose size is in the range of nano, then we can say they are nano. Whose size is in the range of micro, we can say they are micro. Um, is that, I don't know, is that that is the answer he is expecting, or he is asking something else? I don't know.
Professor Samba Obulash, if you want, you can elaborate your question. You can unmute yourself and you can speak.
Yes, sir. Please, sir. That will be good.
Hello, good evening, sir.
Yes, sir. Please.
Sir, I'm asking that the practical examples of this micro and nano sensor using nowadays, sir, where they are using now.
Okay.
You mean traffic signals or something, na?
They are all optical, actually, basically electrical signals. They are not optical, basically. No way they are connected. Yeah.
Okay.
A kind of sensors like pressure sensors will be there, and then acceleration, velocity. These are all different sensors. I cannot distinguish nano or micro kind of things. So if they say, then only we will know that it is a micro or nano or kind of things. What type of material they are using.
Sir, one more question is, nowadays we are using mobile phones, sir, smartphones.
Yes, sir.
Sir, in this also there are some sensors, sir.
Exactly. Pressure sensors are there. When you touch, screen will open. They are the pressure sensors.
Only pressure sensors, or is there any other sensors available in the
lot of sensors might be there, because when your GPS connection will be there, like when you are using an app called like a Strava app, when you are moving, when we are running, when you are heartbeat kind of things. There are different types of things are there, like when you are keeping watch and connected to that, and there are like our heartbeat rate kind of things. There are different types of sensors the possibilities are there, sir.
Sir, is proximity sensors available in mobile phones, sir?
Is
proximity sensor, sir?
I don't know that word exactly meaning
proximity
of that.
And non-proximity sensor, sir.
Sorry, sir, I don't know that actually.
Okay, sir. Thank you.
Thank you, sir. Thank you very much.
Thank you, sir. Another question from Professor Hammond. Is there any easy method for prepare graphene layer like 1x1 meter size?
Sir, graphene can be prepared in two methods. One is physical, another one is chemical. Physical method is possible, sir, layer by layer. But in chemical methods, it is not possible. A few layer graphene could be prepared. But in case of physical method, it is possible. 1 layer, 2 layer, 3 layer, like that.
Thank you, sir. Another question from Professor Sandeep. How graphene is available in market?
Means how available means I am not getting. Means they are asking the companies which will supply graphene or what?
Yes, sir. I will ask the Professor. Professor Sandeep, you can unmute. You can elaborate your question, sir, please.
Sir, I want to. Which company provided graphene? Actually, I want to use it for machining.
Yeah. Dr. Sandeep, almost all the companies, chemical companies, are supplying the graphene actually. Like Merck company, and then different chemical supply companies will be there. They are supplying this graphene actually.
So actually, I want to use it for machining purpose, for cooling purpose.
Yeah,
means,
you can.
As a coolant.
You can purchase. Otherwise, also you can prepare also. Humus method will be there.
Okay.
And little like there you need to use a lot of sulfuric acid and hydrosulfuric acid, like acids and bases you need to use. It is like a tedious process, and you could only prepare minimum 1 gram, 2 grams like that. If you want to purchase, you can purchase that.
Thank you very much, sir.
Thank you.
Thank you, sir. This is another question from Professor Abhishek. Sir, could you give a working example of thin film temperature sensor?
Thin film temperature sensors. Might be a lot of temperature sensors might be there in freezers. Generally, thermocouples will be used in temperature sensors, basically. What I don't know what his meaning of thin film. If he is here, he can unmute and ask me clearly, sir.
Professor Abhishek, sir, you can unmute and you can elaborate your question, sir. Professor Abhishek, sir, I am requesting again, sir. Sir, okay, sir, no problem. We will go with another question, sir.
Yeah.
This is another question from Professor Naresh. Can you please suggest biodegradable and directly available from nature polymer? Have encapsulation. Here I have encapsulation. What is the best
Yeah.
method to have large quantity of core in a capsule?
There might be a lot of biopolymers are available. Naming might be a tough task for me. I can't remember that names and I can't tell. But if you search, there are a lot of biopolymers are available, sir. Actually, a lot of biopolymers are available.
Thank you, sir. You have answered a lot of questions. Sir, yes, please.
So this is Naresh, sir. From research
Hi,
college
sir.
from
Hi,
Bitpila.
Naresh Garu. Hi, sir.
Hi, sir. Namaskaram, sir.
Namaste,
I
sir.
am research scholar from Bitpila Airways campus, sir.
Okay.
I am myself only posted that question, sir, regarding
Yeah.
shell core
Okay.
structure.
What do you mean by thin film sensor? Like you are telling something like temperature sensors? You work on thin film temperature sensor or what?
No, sir, not simple, sir. Just a question, core shell structure and biodegradable polymer. I asked, sir.
Oh, biodegradable things. Yeah. I can't name the biodegradable things, but there are a lot of things are there in the literature. You can search, I think, actually. I cannot name that one at this point of time.
Okay, sir. I will be in touch with you to get that information if any required.
Thank you.
Sir,
Thank you very much.
One more question, sir.
Yes,
Sir,
please.
You in your presentation you shown core shell structure to
Yes.
identify the glucose level, right? Core shell
Exactly.
structure.
Exactly.
So I think you put material inside the capsule and you try that. In the same way,
It's not inside. We synthesized a material such that core and shell will be designed like that. We prepared a material where core and shell will be there, which is in the range of nanometer scale. That material we use for glucose sensing and for non-enzymatic sensing, actually.
understood, sir. But, similar way of synthesis I am doing for my research, sir. I am working.
Okay, fantastic. Yeah.
Thermal energy storage, sir. Thermal energy storage application.
Okay, thermal energy storage. Okay, got it.
So I will be working with phase change materials, sir. So I'm working with phase change materials for doing that, sir. Thermal energy storage.
Very good. Yeah, I understood that.
So my task is to now encapsulate the phase change material in a polymer shell, sir.
But polymers don't withstand for high temperatures. Do you know that? Am I right?
Yes, sir. For my application, I don't have any high temperature, sir.
Okay.
It will be less than 60 degrees.
Then it is possible, I think, actually. But you need to search some of the things, actually.
Yes, sir. So what I'm facing the challenge is unable to come up with a more content of core, sir. So
That is a tough task, actually. That is really tough task because you need to have a lot of chemistry knowledge. How it comes like core kind of shell kind of thing is you need to have basic reaction understanding and chemistry understanding, pressure, temperature, and time, and then chemicals you are adding. These are all the 4 parameters you need to recheck it and recheck it and recheck it. You have to do repeatedly.
Yes, sir. I've been working on this method since 1.5 or 2 years, sir. So I've been successful. But any best method you able to suggest, sir, to prepare this kind of capsules?
Yeah. We can have a discussion. We will meet and talk because this is like a very general place. Like I will share a mail ID with the concerned people. Otherwise, I am putting my mail ID in the chat box. You please mail me. I'm giving my mail ID here.
Definitely, sir. Sir, one more question, sir.
Yeah, please.
Regarding XRD, sir. XRD, I will be doing XRD calculation for my materials, sir. So my question is, after doing XRD test, you'll be getting result, right? XRD peaks. So how to identify the particular peaks? So you'll be getting some 002, 001, 101 like that.
Yeah. That is the Miller indices peaks. Actually, whatever material you are preparing, like let us say you assume you prepare ZNO.
Yes, sir.
And then you have to check for JCPDS data, which will be available wherever you are doing your X-ray diffraction, where you are giving.
Only, sir.
Okay, you ask that concerned person to match the peaks. Actually, that is one way.
Okay.
And they can match it. If your material is, you are preparing an entirely a new type of, I don't think so you will be preparing an entirely a new type of material, surely. You will be matching somewhere, some point. There may be angle, 2 theta differences might be there, some intensity differences might be there, peak broadening might be differences are there due to the diffraction phenomena of particular prepared material. It is required some, like I will give you, if you mail me, I will give you one paper. Even in, you can search in my Google Scholar, which has got very high citations, like 240 citations, or like 130, 230, I think 230 citations are there for that paper. It is X-ray calculations for some particular material. What all the calculations you can do, we wrote a one paper, and it is there in the Google Scholar also. You just type my name in Google Scholar, you will get that, and you see that, I think you will understand.
Sure, sir. Thank you, sir. Thank you very much.
Thank you very much, Naresh. Thank you. I posted my mail ID in the chat box. You can use it and mail.
Thank you, sir. One more last question, sir. What is the future career in nanomaterials after graduation?
I advise at the level of post graduation and at the level of PhD only nano specialization. At the level of undergraduation, I don't advise anyone. There is a good scope is there. People are doing it. And here there is a small problem is there. If you are thinking normally like all other, like a software job or a teaching job kind of thing, then it may not be suitable for you. If you are thinking something differently, like one mechanical student is there with me who completed his MTech with 9 publications in the MTech. And now he got 2 UK opportunities and he's going for PhD in UK. One more student is there who is going to join in metallurgy department, materials and metallurgy department in IIT Mumbai. Kind of, it's all like his student passion. If they have interest, surely everywhere there is an opportunity, surely will be. That is what my feeling.
Thank you, sir. Now I will proceed with vote of thanks, sir.
Thank you. Thank you very much for the opportunity given.
Thank you very much, sir, for your excellent presentation session. It is really very informative session, sir. You have started with the nanoparticles and various applications, nano-sized particles and its properties, the importance of quantum effect with interesting practical applications, biomimicry like hydrophobic surfaces, and nanosensors with the example of self-driving cars, sensors and actuators, gas sensors, mechanism of sensing like observation gas, and the properties of parameters and sensing materials, chemical sensor working principles, challenges and objectives, and case studies with the sensing properties and gas sensor characteristics, and on the last, cyclic voltammetry. Excellent presentation, sir. Thank you very much, sir. It is a really very detailed and informative session, sir. Thank you, sir. Now I request our participants, you can find the feedback form in the chat box. You can give your feedback for the administration purpose. Our today's session is over. Tomorrow we will start with, as usual, 9:45. Yeah. Yes. Our tomorrow morning session topic is production and the characterization of silver nanoparticles. From Professor Sadasivappa, and the afternoon session topic is X-ray magnetic circular dichroism study of magnetic materials using thin films. Professor Vijay Raj Singh from University of South Bihar, Gaya. Thank you very much. Thank you to all the participants. We will join tomorrow. Thank you. Thank you very much.
Hello, sir. Hello.
Yes. Tell me.
Sir.
May I know who is speaking? Please introduce yourself and then speak, sir.
Yes, sir. I'm Sharad Chandra from Nanostructures Engineering College, sir.
Okay.
Actually, in phase 1 of STTP, we didn't got any materials, sir. At least video lectures for further reference.
See, the first phase material, they are not, the resource persons, they are not given the materials. That recordings are available with the YouTube link.
YouTube. Hello, sir.
Yes, tell me.
Can you take the YouTube link, sir, in a mail? or WhatsApp?
Charan, you post YouTube link of the phase 1,
Okay,
this one, STTP program,
okay,
the chat box.
okay, sir.
And one more thing, sir. As we requested in phase 1, yeah, this STTP is really nice, sir. Phase 2 is nice. At the evening session, it was with experimental analysis and experimental how to do experiment. All those things are there, and I really appreciate the things, sir. Thank you, sir.
Okay, thank you. Once again, all the participants I am requesting, so everyone should mute your microphone and video during the session and don't present your screens. I am seeing some people, they are laying on the bed and switching on the camera. It causes inconvenience to other people. Please, if you do like that, we are not going to allow you for the next sessions. My sincere request is, so all our professors, assistant professors, research scholars, and PhD holders, please understand the difficulty. Okay, it should not cause inconvenience to other participants. Okay, some people, they are laying on the bed and listening this one session. If you listen like that, don't worry, but you should have to mute your video and microphone. If you do like that, we are not going to allow you for the next sessions. Charan, who are doing like that? Just inform the names. Charan, inform that names. Next time, we are not going to accept that type of behavior in the
Dilip
session.
Malhotra.
Yes?
Dilip Malhotra.
Dilip Malhotra. So please respond, sir. It's not good on your part. See, there are lot of people are there with high profiles. Should not do like that. Again, other ones.
Mr. Syed Sharma.
See, it's a common announcement to everyone. Should not do like that from the tomorrow session onwards. From tomorrow onwards. Please cooperate with us for the smooth conduction of this program.
Sir, I had one doubt.
Tell me.
In a feedback chart in organization, what we feel, sir, SV college or our studying?
See, it's your affiliation. You should have to fill your affiliation, not our college name.
Okay, sir. Thank you, sir.
So one more thing is, I have registered with my Yahoo ID. So but Google Meet is working with my Gmail ID. Actually, that is not working with the Yahoo ID. So I think you have sent a message that the participation ID should be same. But I am facing